Hello everyone, my name is Katrin Mäger and I will go over the main points of our paper titled The Fire Design Model for Timber Frame Assemblies with Rectangular and I-shaped Members as part of this webinar. First, let's look at timber frame assemblies, which are a type of lightweight timber structure. The timber elements usually have relatively small dimensions and are made of sawn wood. They may also be made from laminated veneer lumber or I-joists, and the latter is something that we will cover in this presentation as well. A timber frame assembly usually has claddings or coverings on one or both sides, forming cavities, and these cavities may be fully or partially filled with insulation material or left empty. The behavior of these surrounding materials affects the charring of wood. Next, let's look at how we are able to consider the contribution of different insulation and cladding materials. That can be done using the effective cross-section method. In principle, two phenomena occur in fire. The wood chars, which reduces the cross-section, but also the mechanical properties of timber degrade at elevated temperatures. Charring may occur on the exposed sides and the lateral sides. In the effective cross-section method, the loss of strength and stiffness is considered by an additional fictive charring depth, called the zero strength layer. The effective cross-section obtained from the method has a similar shape to the initial and the same strength as at ambient temperature. This principle makes the method easy to use also in hand calculations. The effect of different materials is considered by using charring factors, which alter the charring rate. The graph on the left represents the development of the char depth on the exposed and the lateral sides of a rectangular timber member. On the right is shown the charring of I-shaped members, with the solid line representing the exposed side and the dashed line representing the lateral sides. The different charring phases, shown with different slopes, depend on the protection offered by the surrounding materials. The equations to calculate the effective cross-section are developed based on furnace fire tests and thermal finite element simulations. The design model for rectangular members was developed by Mattia Tiso as part of his PhD project. He also developed a qualification methodology for insulation materials. This allows the engineer to consider the protection offered by insulation materials based on their performance and not only the source material, because previously we used to differentiate mostly only stone wool or glass wool. More recently, the topic of my PhD project is to adapt the effective cross-section method also to I-shaped members. The equations are slightly modified to cater to the specifics of the I-joists. Most notable differences are that lateral charring may begin before the fall-off of the protective claddings, and the additional need to consider the charring of the web. Finally, I would like to leave you with some points of discussion. It is important to provide the practicing structural engineers with reliable and usable design methods. Fire tests show that the greatest impacting factor for the fire resistance of timber structures is the protection offered by the first layer on the fire side. That means that, for example, the ability of a gypsum board to stay in place for a long time has a great influence on the total result. The design methods presented here are able to consider that, along with the contribution of the insulation materials. The effective cross-sections are simple to use in further load-bearing analysis. Of course, further research is always needed, mostly in terms of expanding our knowledge about newer or bio-based insulation materials. The design model for I-joists can also be extended, for example, to also consider metal webs. I hope this short overview has been enjoyable, and thank you so much for your attention.